Okay, so today, after seeing, sort of writing your first quantum program that you did just now, so we were talking about quantum programs of single qubits, so single qubit quantum gates. We finally move to the case of multiple qubits. So, running a sequence of quantum gates on a single qubit, although it's instructive and it can buy us some advantage, for example, as you've seen for the firework puzzle, it doesn't really harness the full power of quantum computations, right? Just like in the classical case where, your computations are usually manipulating, millions of bits or more. Complex quantum computations require multiple qubits. Okay, so the summary for this section is we will formally see what states of multiple qubits are. Then we will look at 2-qubit gates or 2-qubit states as a sort of special, simpler example, and then we'll sort of kind of generalize this naturally to more than 2 qubits. Okay, the general case of n qubits. Yeah, so as I said, right, we really need multiple qubits to really harness the power of quantum computations. And in the case of classical bits, remember that a single bit had 2 possible values, obviously 0 and 1. For 2 bits, there are 4 possible strings of 2 bits. That's 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and to make sort of the analogy with the qubits and the quantum case, the two sort of the single qubit case, the standard basis elements were ket 0 and ket 1, right? And for multiple qubits, we will postulate that the standard basis elements, much in analogy with the 4 possible classical values of 2-bit strings, will postulate that for 2 qubits, the standard basis element will be 0, 0, ket 0, 0, ket 0, 1, 1, 0, and 1, 1. In particular, we will think of the standard basis elements here as standard basis elements of a 4-dimensional space, right? It's 4-dimensional because you can sort of represent these 4 basis states as, vectors with 4 entries, and, 0, 0 will be the vector, 1, 0, 0, 0. 0, 1 will have a 1 in the second place, etc. Okay. So a state of 2 qubits formally is a superposition over the standard basis elements, the 4 standard basis elements, and it's specified by 4 amplitudes, right? 1 for each possible basis element. So in general, a state of 2 qubits takes the form, A0, 0 times the first basis element, and A0, 1 plus 1, 0, so A1, 0, and then plus A1, 1, as you can see here. Okay, we can interpret this as a 4-dimensional vector, and we write it so in the column vector form like this. And again, of course, the amplitudes are complex numbers. Okay, just like in the qubit case, this A00, A01, etc. They're complex numbers, and we still have a similar requirement as we had before. Remember, in the qubit case, we required that the norm of the vector for a qubit state, the norm of that vector was 1. And we'll have a similar, well, the same requirement here. The norm of the of the vector should also be 1. So does it make sense why a state of 2 qubits is a vector in 4 dimensions? Before we proceed further. Sai says yes. Good. Very good. Okay. So it's a very natural generalization, right? You're just a superposition over all possible classical strings. That's the way to see it. So now we come to the next sort of natural question, which is, what if we want to combine 2 single qubit states? Okay, suppose I give you, one qubit, the qubit 1, and qubit 1 is in an equal superposition of 0 and 1. Okay, and then I give you qubit 2, which is in the state 0. Okay, what state does, formally, what state does this, do these 2 qubits form as a 2 qubit state, as a vector in 4 dimensions? What state do these 2 qubits form? This is the question that I ask you. Does the question make sense? Before we said, states of 2 qubits, they are superposition over, the 4 standard basis elements. Okay, so now I give you qubit 1, qubit 2. I tell you what state they're in. What is the global state of the 2 qubits? Anyone have a guess? I want you to write the state of these 2 qubits, qubit 1 and qubit 2, in this form here. Either this form here where you're specifying the amplitudes, the 4 amplitudes, right? Either in this form or in the vector form. Basically, I want you to tell me what are the 4 amplitudes if I were to specify this state of 2 qubits, which ought to be a valid 2 qubit state. What would the 4 amplitudes be? Any guesses? So, okay, Lorraine is suggesting that the state of the 2 qubits is 1 over square root of 2, 0, 0 plus 1 over square root of 2, 0, 1. Okay, Jacob is suggesting 0, 0, 0, 0, 0, 1, and 1, 0. Okay, any other guess? Okay, so actually, Mihir has the correct answer. It's very similar to what Lorraine said, except Lorraine has a 0, 1, it's a 1, 0. Okay, so here's how to see it. So, we would like to write something of this form, right? We put the first qubit, next to the second qubit. The way to understand this is that sort of the first qubit was in an equal superposition of 0 and 1. The second qubit was always in the state 0. Okay, so in our universe, if you think about it, there are 2 sort of worlds, 2 branches, right? There's one branch in which the 2 qubits are in the state 0, 0. There's one branch in which the 2 qubits are in the state 1, 0. Okay, so the overall state, let me write down this calculation. So, we had the first qubit, which was 1 over square root of 2, 0, plus 1. And then the second one, which was just 0. Okay, the way that we sort of extract a valid 2 qubit state, the 4 amplitude, is we simply apply the kind of the distributive law, if that makes sense. So we multiply the 0 and the 0. Multiply, I mean, we just sort of pull them together in a very natural way. Sorry, let me write it like this. Okay. Right, so I'm combining first this with this, and this gives me this one. And then I'm combining this with this, and this gives me this one. Okay, that makes sense. So whenever you have, good. So whenever you have two qubit states, each of them separately is well defined. You simply apply, distributive law, multiply out, in some sense, quote unquote, and then this is what you get. What determines the sequence? Very good question, because there was some confusion. I think Lorraine had said 0, 1. So yes, so it's like distributing. Yes, so to answer Ashley first, it's like distributing the 0 to the 1, the 0 to the 1 and 0. Yes, exactly. So to determine the sequence, well, you have to keep the same order that you had before, right? So the first qubit is in state 0, gets paired with the second qubit with 0, so it becomes 0, 0. Okay, and now for the other branch, you have the first qubit in state 1, right? And the second qubit in state 0. So you have to keep the order. That's why it's 1, 0. Because the first entry is always the first qubit, the second entry is the second qubit. Okay, so from now on, we will be using, not just the notation like below, not just sort of this notation here, but we will also be using this notation here. And we interpret it to mean exactly the second thing, okay? So whenever we write from now on, psi 1, psi 2, okay? Let's say that psi 1 is equal to, alpha 1, 0, plus beta 1, 1. Let's say that psi 2 is equal to alpha 2, 0, plus beta 2, 1. Okay, from now on, whenever we write psi 1, psi 2 in this form, what we mean is exactly this. So alpha 1, 0, plus beta 1, 1. Okay. And we distribute things. Okay. So to answer Shriyan, so the number assigned to qubit isn't interchangeable. No, it's not. It's not. I mean, you have to keep an ordering to know, well, to know which qubit is which. Just because, later you might do things to these qubits, you might apply gates to them. So you need to know which is the first qubit. When you apply your gate, you want to say, my gate X on the first qubit and the fifth qubit, for example. So you have to keep a track of the order. So we know what 0 means, but what does 0, 0 mean? Okay, good question. So that we have answered at the start, right? So 0, 0 is this very well-defined thing. Let me go back. 0, 0, Lukman, is the standard basis element of a 4-dimensional space. So 0, 0 is a very well-defined thing. It's exactly the standard basis element of the 4-dimensional space. Yes, very good. So that's why, if I wrote things in this form here, right, in terms of the standard basis of four-dimensional space, there's no, ambiguity as to what I mean. I mean, a four-dimensional vector, but the ambiguity arises, that's the reason why I brought it up. The ambiguity arises when I say, I have the first qubit and the second qubit, and I want to put them together. And now this first line here, the first line here, this is not well defined, because I want to interpret it as some kind of four-dimensional vector, but this first line here, when I'm putting them in product, it's not really in terms of the standard basis, so I don't know what it means. And so that's why I'm telling you, we'll use this notation to mean precisely the bottom line, where we distribute things and we write it in terms of the standard basis element of the four-dimensional space. Good. And so far, I mean, nothing super fancy. Just establishing some notation and sort of some very natural notation. So the order of 0 and 1 when distributing goes from left to right. Yes, yes. Mm-hmm. So this is a general combination of two single qubit states. So let's do an exercise. Oops. I don't know why exercise here is so tiny, but okay, let's try an exercise together. So you're given two qubits. The first is in the state 1 over square root of 2, 0 minus 1. The second qubit is in the state 1 over square root of 2, 0 plus 1. What is the joint state of the two qubits? You can, type your option 1, 2, 3, or 4 in the chat. Okay. So we started off with 3, 3, 3, and then somehow the community changed its mind and it's been 2, 2, 2, 2, 2. So in fact, the answer is 2, because you have the 0 going with the 0 and it's a plus. You have the 0 with the 1, so that's 0, 1, it's another plus. Now you have the minus 1 going with the 0, that's a minus 1, 0. And you have the minus 1 going with the plus 1, so that's another minus 1, 1. Good. So it's answer number 2. Let's try another quick one. Okay. This one, I haven't told you the rule yet. I want you to sort of guess what the rule will be. So I don't know what foiling is per se, but I think that yeah, it is like in algebra when you multiply out. It's like the distributive property. Okay, so good that Ashley knows about this. So suppose now we initialize two qubits in a state 0. So the joint state of the system would be 0, 0. And by the way, just as just a kind of recalling, whenever we write, just by the rule that the notational rule that I said just now, if I write 0, 0, right, what this means is 0, 0, right? Just as an aside. Okay, so now the joint state of the system is 0, 0. Suppose we then apply an X gate to the first qubit. What is the new joint state of the two qubits? Yeah, so it should be pretty clear that even though we haven't defined the rule formally, it should be pretty clear that our rule should have number 4 as the correct answer. So that is indeed the case. Okay, so we'll see in a moment. We'll get to this in a moment. But it is number 4. Right, the X gate is acting on the first qubit, and then it does nothing to the second. Very good. Okay, so now, I've defined this notation of, you have a qubit in the first, qubit 1 and qubit 2, they're in the state psi 1 and psi 2, and, I can write them as psi 1, psi 2. Yeah, we talked about this notation. Now, the question I have for you is, can any state of 2 qubits be written in this form? Okay, let's say, let me make this question a little bit clearer. Let's say I give you, a state of 2 qubits, and so this state here, I give you this state here. Okay, is it true? And I ask you, find, psi1 and psi2. This should be single qubit state, such that psi1, psi2 is equal to psi1, psi2. The question I have for you is it always possible to find such psi1, psi2? Shreyans believes no. Zach thinks no. And why do you think or believe that that is no? If it is no. Yeah, so okay, so Shreyans has a good sort of intuition, which is that it's always possible to go in one direction, right? You can start with 2 single qubit states, and of course you can go forward in some sense and determine the A00, A01, A10, A11. If you start from these 4 coefficients, it's a bit unclear how you go back to the single qubits one. That's true. Doesn't mean they don't exist though. It's unclear how you get there. From psi2, you should get 4 equations. From psi1, 2, you should get 4 equations, which are solvable for 4 unknowns. Yeah, so see the problem here. The problem, I think, might be that you have actually, remember that there are these constraints on the norm of the vector being 1. So we want the vector of 2 qubits to have norm 1, right? So we have 4 equations here. If we were to try and find alpha 0, the 4 coefficients of the single qubit states, but we have 2 additional constraints for the norm of the 2 single qubit states, right? We have 2 norm constraints. So actually there might be more than 4 equations. Does that make sense? Because you have to satisfy the norm of the single qubit states. Both of them have to be 1. So, okay, so it's good that you thought about this. The answer is that no. So it's not true that all states can be written in this form. So the states that can be written in this form are very special, and they're called product states. They can be decomposed as such. The ones that can't are called entangled. Okay, entangled states are states that cannot be written as a product state. So what I ask you to tell me now is, can you give me an example of an entangled state? So a state that cannot be written as a product state. Any thoughts? Okay, it is not an easy question to come up with such a state, even though actually remarkably, overwhelming majority of states that you can write down will actually be entangled and not product state. So if we took, 4 kind of random coefficients, such that the vector has norm 1, this 4-dimensional vector has norm 1, it will, with overwhelming probability, be an entangled state. So product states are actually very few. So actually, before we move to measurements of 2-qubit states, let me give you an example of a state that is entangled. Okay, and actually, I want to answer Fauzan's questions because, more properly, because it's a good question. So here's an example of a state that is entangled. It cannot be decomposed as psi1, psi2. Okay. So the exercise before was a challenge exercise. It also asks you to show, not only give me an example, but I want you to prove to me that this state cannot be decomposed in 2 ways. So let's try, Fauzan's approach. Okay. So, of writing these 4 equations and 4 unknowns. Okay. So let's see, psi1, let's call it alpha 1, alpha 1, 0 plus beta 1, 1. And then psi2, let's call it alpha 2, 0 plus beta 2, 1. Okay. So now what we want is, psi1, psi2 to be equal to the state that we have above, which means that we would like, alpha 1, alpha 2, 0, 0 plus alpha 1, beta 2, 0, 1 plus beta 1, alpha 2, 1, 0 plus beta 1, beta 2, 1, 1. We would like this quantity here to be equal to this. And the question is, can we find any values of alpha 1, beta 1, alpha 2, beta 2, for which this can happen? Okay, so let's write the equations as Fauzan was suggesting. Remember, we have additional constraints here, right? So let me write it here. So we have these additional constraints that, alpha 1 squared plus beta 1 squared should be equal to 1. Also alpha 2 squared, sorry, the magnitude.
I think you have to scroll down, Andre.
I have to scroll down. Oh, I went to the next page. Sorry, guys. There you go. There you go. Thanks, Jason. Okay, so these are the constraints that I have. And now the equations that I would get from here, I don't know how to copy it, but let me just write the equations that I would get. So I'm just matching coefficients, right? I need, actually, let me rewrite it because I think that would be more helpful for everyone. So this we want it to be equal to 1 over square root of 2, 0, 0. Let me write it very explicitly, plus 0 times, 0, 1, plus 0 times 1, 0, plus 1 over square root of 2, 1, 1. Okay, so now I'm matching the coefficients. I want to match this one with this one. I want to match this one with this one. This one with this one, and this guy with this guy. Okay. So now if you write the equations out, You get this. Okay, then we have alpha 1, beta 2 to be equal to 0. We have alpha 2, beta 1 to be equal to 0. And we have alpha, sort of beta 1, beta 2 is 1 over square root of 2. So from these two equations, we get that, you know, 1 of alpha 1 and beta 2 has to be 0. 1 of alpha 2 and beta 1 has to be 0. Okay. I mean, there are a bunch of cases that we can see here. Let's see what at least one of the alphas and one of the betas has to be 0. One of the betas, let's see. So if alpha 1 is 0, then alpha, okay, then you're kind of, yeah, that's true. Yeah. So the problem is, you know, either one of alpha 1 or beta 2 from this equation here would have to be 0. Okay, but then, you know, if it's alpha 1, it means that this quantity here would be 0. So it cannot be equal to 1 over square root of 2. And if it was beta 2, which was 0, then this quantity here would be 0, but it has to be equal to 1 over square root of 2. Okay, so this is how we prove that it's not possible to write this as a product state. So there's this state here is very special. It's called, so this state that we have here, it's called an EPR pair. It's in fact, it's maximum entangled. We'll see what that means later on. It's a very special state. Okay, let me go back to the slides. Hopefully that example makes sense. Is there anything that I can clarify before I move on? So I think the point, Fauzan, is, you know, where the intuition failed is that these are not linear equations, right? Because I also have kind of multiplications. It's not just a linear thing. So it's not true that you always have a solution. Right, I can always write a system of this kind. Well, you know, two equations in two variables, you know, and I ask you xy equals to 0, sorry, here. And then I ask you xy is equal to 1. Right? So obviously this has no solution, but it's two equations and two variables. Yeah, Jason's comment also makes sense. That's why most states actually are not product states. But this is sort of to answer the intuition of Fauzan. Even with two equations and two variables, if there are products, you might very easily be unsatisfiable. Okay, so back to measurements. Lorraine, what does it mean to be a product state physically? Being a product state physically means that, you know, perhaps you've created these two qubit states independently from two different labs, two completely independent processes. And the two qubit states will be completely uncorrelated. That's how they are in a product state. They were created without correlation with each other, basically. Okay, so measurement of two qubit states. Okay, a measurement on a state of two qubits correspond to asking the following question. Is the state of the two qubits 0, 0, 0, 1, 1, 0, or 1, 1? These are sort of the classical bit strings in some sense, right? These are the classical states. So Bourne's rule for two qubit states is very similar to the case of single qubit states. So again, the probability of 0, 0 will just be the 0, 0 amplitude. You know, you take the modulus and you square it. Similarly for all the others. Just a natural generalization to 4 dimensions. And the requirement, again, because the probabilities have to sum up to 1, is that the modulo square of the amplitudes sum to 1, meaning the vector has norm 1. Hopefully this is quite natural. Yeah, as we have discussed, one of the most famous 2-qubit states is the Bell pair, which I showed you earlier. And here is how we prepare this very special state. You'll see how special it is in probably next week, in one of the modules next week, when we do teleportation, quantum teleportation. So here's how we prepare it. So we can start with 2 qubits initialized in sort of this 0, 0 state, this classical state. And then what you do is you apply a Hadamard gate, a H gate to the first qubit. So, if you were to write in a program, this would be circ.h00 for the 0th qubit. In Python, you start counting from 0. Then you apply a C0 gate from the first qubit to the second. Okay. And let's draw the circuit. So I'll tell you in a moment what a C0 gate is, because you haven't seen what that means. But for now, let's just create an EPR pair. And so this circuit here creates an EPR pair. It's very simple. You do a Hadamard and a C0. And then, as you can see, if we measure the 2 qubits, oh, somehow this is not scrolling for some reason. Now it's scrolling. So if you measure the EPR pair, what you expect to get is obviously, with half probability, you're going to get 0, 0. With half probability, you're going to get 1, 1. Right? The EPR pair was just an equal superposition of 0, 0 and 1, 1. Yeah. So hopefully this makes sense. Okay, now one natural question that you might have is it possible, I give you a 2 qubit state. Is it possible to measure, just a single qubit out of the 2 qubit state? I mean, certainly this, this should be included as a possibility in our theory, in our formalism, because, as I was saying before, you could be creating the first qubit in one lab, the second qubit in another sort of completely independent lab. Of course, it makes sense to consider the state of the 2 qubits, but they're kind of independent, right? They're in a product state. And of course, each lab can decide to measure their own qubit. So if the theory of quantum information wants to be kind of complete in some sense, it has to, at least account for something as basic as this, 2 labs creating independent qubits, measuring them independently. So, yes, so I guess I've answered already my own question. Is it possible to measure just a single qubit out of a 2 qubit state? The answer is yes. Okay. I guess the question that I can ask you before I reveal the answer is, how do we do this? What is the process for measuring a single qubit out of a 2 qubit state? So let's say that, I have this state here. I want to measure the first qubit. Wouldn't it affect the other? Well, Luckman, it shouldn't affect the other, right? I mean, they were created independently in different labs. They're completely uncorrelated. It should not affect the other qubit, in my view. Like, after the measurement, for instance, what I mean by shouldn't affect the others, after the measurement, they should still be in a product state. That's what you would expect, right? So what I want you to tell me or to guess is, what are if I measure the first qubit, right? I'm going to get one of 2 outcomes, right? 0 or 1, because I'm measuring a single qubit. I want you to tell me what are the probabilities of getting answer 0, what are the probabilities of getting answer 1, and I want you to tell me what is the state of the 2 qubits after I've made this measurement on the first qubit. These are the things that I want you to try and guess. Can I go again? Yes. Okay, so I give you a 2 qubit state, okay, and I ask you what happens if I measure qubit 1. So I have qubit 1 and qubit 2, state of 2 qubits. I ask you what happens if I measure qubit 1. Okay, so what I want to know is, presumably when I measure qubit 1, I'm going to get an answer. Either the first qubit is in state 0 or is in state 1, right? Just like it would happen if I measured a single qubit state. Okay, so what I ask you is for you to tell me what is the probability that when I measure qubit 1, I'm going to get outcome 0? What is the probability that I'm going to get outcome 1? And moreover, what is the state of the 2 qubits going to be after I've performed this partial measurement on just the first qubit? And this should be something that our theory is able to predict. It's such a basic thing because, I could have a lab in New Zealand preparing a qubit. I could have a lab, in Italy preparing another qubit. You can definitely talk about the global state of the 2 qubits. That makes sense. And it's certainly possible for the lab in New Zealand to measure their own qubit and get an outcome 0, 1. But what are the probabilities? And in particular, what if the qubit is not a product state, it's entangled? That's where it becomes maybe more tricky. So Loren has a good guess. So the probability of 0, 0 is A00 squared plus A01 squared. Do you mean, Loren, the probability of 0? Yes, exactly. Okay. Yes, that's actually correct. Okay, do you want to explain the intuition in the chat?
I'll just do it vocally if that's all right.
Yeah, good, awesome.
So basically you're asking what's the probability that that term is going to be a 0? So that means that if you look at the 4 components of it, it would be when the first component is equal to 0. And that occurs for A00 and A01. On the other components, the first output, if you will, is a 1. So all you want is the probabilities related to those first 2 terms, and in order to get those probabilities, you take the magnitude of them. So you square the A00 and you add the A01 squared.
Exactly, thank you. Exactly, Jacob also got, yes, the right intuition. So yeah, so what we do is we look at all the 4 components, which one of those have the first qubit in the 0 state. In this case, it would be this and this, right? Because there's a 0 here, there's a 0 here. And we just square the magnitude of the amplitude. So A00 squared plus A01 squared. And now the probability of getting 1, well, it has to be everything else, right? So it has to be this plus this. Does that make sense to everyone else? Awesome. Very good. Well, so far it makes sense to Andrew. I don't know about everyone else. Good. Thank you. Okay, so then the other question that's left to answer is, what is the post-measurement state? So, after I've measured the first qubit, the first qubit perhaps undergoes some kind of collapse, right? Or the state undergoes some kind of collapse. I still have 2 qubits, right? What is the state of the 2 qubits after the, let's say I obtained outcome 0, okay? I've measured the first qubit and I got outcome 0. What is the state of the 2 qubits of condition on getting outcome 0? Yeah, that's correct, Kieran. So they're exactly a superposition of 0, 0 and 0, 1. And that is because the state of the 2 qubits collapses to the 2 components in which we have observed, in which a 0 was present on the first qubit. Okay, so if we obtain outcome 0 for the first qubit, we look at which components had a 0. In this case, it's the first 2. And we simply, the state after the measurement simply collapses to just those 2 components. Okay. So here's a recap. Basis elements 0, 0, 0, 1, 1, 0, 1, 1. 2 of them are such that the first qubit takes the value 0, 0, 0, and 0, 1. 2 of them are such that the first qubit takes the value 1, 1, 0, and 1, 1. Probability of obtaining outcome 0 is this. Outcome 1 is this other. And the post-measurement state collapses, well, after the measurement, the state collapses to a superposition of just 0, 0, and 0, 1, if I've obtained outcome 0. Okay. Now, is there anything wrong with what I wrote with this state here, psi prime? Is this a valid state? I mean, our intuition was certainly valid. I think all that we said was very natural and made sense. However, is this state psi prime? Is there anything wrong with this state? I see. So what you're suggesting is we should sort of write it, like this, basically. 0, because we've already got it, times A0, 0, 0, plus A0, 1.
No, you wouldn't use the ket notation because you've already collapsed that state. So it's now a classical bit, not a ket.
Okay. So you bring up a good point. So maybe I should clarify this, right? So in our, I guess, theory, in our formalism, classical states are like special cases of quantum states. So it is true. I mean, intuitively, I've collapsed it to a classical state. Classical states are still allowed in quantum, in our quantum sort of information theory. These are just special cases of classical states. So 0, if I write 0, you can think of this as the classical state 0. It's always 0. If I measure it classically, I will always get 0. So this is intuitively the classical 0 state. But there's not a special sort of when we have the formalism of quantum physics, there is not a special kind of way of denoting classical states. This ket 0 state you can interpret as a classical state, but it's just a special case of a generic quantum state, which could be alpha 0 plus beta 1. Does that make sense? Like I can represent classical states just by using kets. Ket 0 would be the 0 classical state, and ket 1. As long as after that I in what way are they classical? In the sense that if I were to perform classical operations on them, okay, for example, the X gate is a classical operation, it just flips the bit, then my 0 would go to a 1, right? So things always remain classical. There's never any interference, you see. It's only when I start doing truly quantum operations like the Hadamard gate, which creates a superposition, that then, things are not classical anymore in some sense. But as long as all of my operations are classical in some sense, like the X gate, okay, then, if I start with a 0 state, I always end up with the classical state 1. There are never any sort of superpositions, let's say. Okay, so the problem, to go back to what the problem was here, problem is this state does not have norm 1, right? The norm of this state is no longer 1, because, I mean, the norm of this state would simply be, hold on, so the norm of this state would just simply be alpha 0, 0 squared plus alpha 0, 1 squared. That's the norm of what we have here. So that's definitely not equal to 1, because before, you know, it was the sum of all the 4 terms, which was equal to 1. Now we just picked out 2, just probably less than 1, the norm. So what we do, what the rule is that we simply renormalize the state. Okay, so the state after the measurement is precisely what we wrote, except we are, you know, multiplying by a factor, you know, that sort of a global factor, which just makes the norm equal to 1 back again. So in this case, the new norm of this vector would be modulus of a0, 0 squared plus modulus of a0, 1 squared. And I simply divide by the square root of this norm of this norm squared. So I divide by the norm, so that the norm, the new norm of psi prime becomes equal to 1. Okay. So I adjust things so that now I'm back to a valid 2-qubit state. So after the measurement, the rule is the original 2-qubit state is kind of projected, collapsed onto the vectors 0, 0, and 0, 1, and then it's renormalized. I mean, another way to think about it is that, you know, we are always requiring that the norm of the states be 1. Okay, that's because we want probabilities to sum to 1. We could, you know, equivalently, there's an equivalent way of putting it, is that all, you know, all states are the same up to a factor. You know, you consider all sets of states that are the same up to a factor, you consider them to be the same state. That's another way to look at it, if that makes sense. So what's the probability of 0, 0? Post measurement, the probability of 0, 0 would be, you know, you would have to square this. It would be a0, 0 squared. It would be this. So let me write it here. I'll go on a new page. Okay, so after the measurement, the state has become a0, 0, 0, 0 plus a0, 1, 0, 1. I've renormalized it. So now the probability of 0, 0, if I were to measure this new state, okay, it will be, you know, okay, let me write this state, even make it even more clear. Okay, what is happening? Right, so this is the same as this, right? Right? So then the probability of 0, 0 by Bourne's rule is simply the norm of this thing here, this whole thing, the norm squared. Okay, if you calculate it, this is exactly equal to this. Makes sense? And then P01 would be equal to A01 squared divided by A00 squared plus A01 squared. And if you sum them, you can see that they add up to 1. Okay. So the probability of 0, 0 is simply whatever proportion of amplitude you have on A00 and whatever proportion you have on 0, 1 is the probability of 0, 1. This denominator here is just, you know, kind of a renormalization thing. Okay, So I think it's a good point to stop. I've gone for an hour or so. Let me answer a couple questions and then we'll continue after a break. Okay, so let me answer. What if A00 and A01 would have different values? Then the probability of states wouldn't equal norm. So before you suggested 50%. So 50% is not true, right? The probability of finding 0, 0 is not 50%. It would be 50% if the norms of A00 and A01 were the same. But when they're not the same, the probability of 0, 0 is this number here. Probability of 0, 1 is this number here. And as you can see, they add up to 1. But they don't have to be a half. Does that make sense? So here I've not assumed that A00 and A01 are the same. Maybe I'm misunderstanding the question. Okay, so let's take, just to clarify, okay, last clarification. When we collapse single state, we would get 0 or 1 basis. So in 2-qubit, we should get only one of those. Okay. Yeah, so okay, so in when you measure a single qubit state, you get either 0 or 1, correct? When you measure 2-qubit states, you get one of the 4 possibilities, okay? That's where we started, right? We started by saying exactly that you get one of the 4 possibilities. But then, this is if you measure both of the 2 qubits. But then obviously a natural question is, do I really have to measure both qubits, right? I could envision preparing 2 qubits separately. It's a valid state of 2 qubits, but then I only want to measure one of them. Okay, so my theory should be able to explain what happens then. Okay, and what happens then is that I simply sort of to understand what's the probability of getting 0 in the first qubit, I look at the terms in the 2-qubit state that have a 0 in the first coordinate. And then I take the magnitude squared of those amplitudes corresponding to those terms. And that's the probability of getting 0 when I measure the first qubit. Now the post-measurement state collapses precisely to those terms that have 0 in the first component. And in principle, it can be 0, 0 and 0, 1, right? Not just either of the two, right? It will be both. And it's not because, it can't be treated as a product state. Even if it was a product state, you would still get 2 terms, the 0, 0, because the 0, 0 and the 0, 1 terms are precisely those terms that have a 0 in the first qubit. So when you measure the first qubit, you have to look at those 2 terms. So that's why it's called a partial measurement. So when you collapse to precisely those things. You get outcome 0, you collapse to precisely those things that are compatible with an outcome 0 on the first qubit. In some sense, it's as if, when you have a quantum system, you get a classical answer. The quantum state collapses to the most general possible state that is kind of consistent with the classical answer that it gave you. If it gives you answer 0 for the first qubit, the only things that will remain are the things that have 0 in the first qubit. Does that make sense? Yeah, that does not affect the second qubit, yeah. But does not affect the second qubit to the extent that, you're not measuring it, but you are throwing out some terms, right? In particular, let me just give the last example. In particular, if you have this EPR pair term here, okay, and I say, I want to measure the first qubit. Okay, so now if I get outcome 0 in the first qubit, there's only one term that is compatible with outcome 0 in the first qubit, and it's this one. Okay, So if once I get outcome 0 for the first qubit, the post-measurement state will become 0, 0, right? It's the only compatible term. And now from then on, if I measure the second qubit, I will also get outcome 0 now. So I have affected, in a way, the second qubit, because before I were even measuring the first qubit, right? If I start from here and I decide to measure the second qubit, I will get 50-50, 0, or 1, right? But now, conditional on the fact that I got 0 measuring the first qubit, if I were to measure the second, I would, of course, we probability 1 get a 0. So we'll get back later to the concept of what does it mean for something on the first system to affect the second. It's a little bit more subtle than this, but so far, at least what I said should make sense.